Hello everyone, my name is Annika, and I'm here to show you hopefully a quick video about how to compute the shortest path algorithm and what this algorithm actually means. So I'll start off with the shortest path algorithm here, the shortest path formulation here, which you can find in section 1.5 of the textbook, page 34. I have it here. Explains this formulation a little bit, but I'll go over it a little bit. So we want to minimize the total cost of edges that we're picking. So this XE here, we have one for every edge, and it's like, okay, we set it equal to 1 if we want to pick that edge, and we set it equal to 0 if we don't want that edge in our path. So I added this little x in here thing that I forgot to add, but we have x is an integer here, and we choose it, if we want it in our path, we choose it as 1. So we want to minimize the total weight of this whole path, but we also want to ensure that for every cut that we have, that we're including at least one edge from that cut in our shortest path. So what does that mean? Well, if I take my pink marker here and I just slap it somewhere on this graph, so say here. So we see that I have S on one side of my marker and T on the other side. So that means this is an ST cut. I've cut off S and T. And now we look at each of the edges that intersects. Okay, so there's this one here, CT. There's also this long one here, BT. So for those, we want to include at least one of those edges in our shortest path, because you can see any path I construct from S to T has to cross one of these two edges at some point to get from S to T. So that's what this part is telling us. And then we see that we want it not negative and we want it to be integer. Cool. So that's our formulation. Now, I'm just gonna do, actually no, I'm not gonna do that right now. Never mind. And I will jump right into the shortest path algorithm. So, we have this thing here. How do we use the shortest path algorithm, or Dijkstra's algorithm? So the first thing we do is we do our first cut, and it's just gonna include S. So this is iteration 1. Our cut just includes S. And now I have to figure out what weight I want to put on this thing. Well, I look at all the lines, all the edges that are intersecting my purple line here. We have this 1 and we have a 3. So now we have to pick the minimum of those two. So we pick a 1. That's cool. That's our edge. That's our width assignment for this cut here, is a 1. So now I've used up all the weight here. So what I want to do is turn this into an arc. It's all used up, so now it's an arc. And then, once I turn it into an arc, for my second iteration, I want to absorb that vertex into my set, so into S. So, we've used up all this. We can't go through this edge anymore, so we need to absorb this vertex, so that we go around it. So that will look like this. Whee! All the way like that. And in our set here, we now have S and A. So now, I look here. Well, we have a 2 there, that's cool. We have another 2 there that's intersecting. And we also intersect this 3 here. But there's already something here. We already used 1 up. So this one is also essentially 2, because 3 minus 1. So all 3 of these are 2. Okay, well our minimum's 2. So I put a 2 there. So that's my width assignment here. And I'm realizing you'll see a lot of patterns going on. I encourage you to try another example for yourself to see that a lot of these coincidences are simply coincidences, but just try more examples if you're not too sure how this works. But we see that with this iteration, we've made a lot of these things into arcs. So we got this one here, turns into an arc. This one here turns into an arc. This one here also turns into an arc. And why am I choosing to go this direction instead of the other direction? Well, that's just because I have A in my set already and S in my set. So we're going from our set S to outside from our set U to outside our set U. So I'm going from S to B. Okay, so I'm going that direction. A to B, A to C. Those are our arcs. Now, what's our next iteration? Well, we can't use this edge anymore. Well, we don't really care about these ones. But we still have to include C, because we can't go through this edge anymore. So we go all the way like that. And we see, because C is in our set, also we need to include B as well. because we've also used up this edge. So our third iteration, we have S, A, B, C, that we've all kind of absorbed into our set U. So now what's our thing on this? Well, we have this edge 4, nothing else in there, and we also have this edge 3. So our weight here is going to be a 3. So, ta-da, 3. And now we have to look at what arcs we have created. So we haven't used up all the weight here, but we did use all of the weight there. So that's an arc. And then our next one, we would just have to absorb T into our thing because we used up the edge. So that's kind of what tells you you're stopped, because you've got like TU absorbed into U, and U is no longer an ST cut, because S and U are both in the same thing. So that's cool. We can stop our algorithm, but now what does this tell us? Well, we want to sum our total weights here, and this sum here is 6. So we know that from the weak duality, if we find a shortest path that has length 6, that is optimal, because this part here, this is our upper bound on all the lengths of paths here. So, oh no, this is our lower bound, my bad. So we cannot have a path that is shorter than 6 here. So if we find 6, that's optimal. But how do I do that? Well, this algorithm is pretty convenient because it kind of shows us where we are. So we look through all these arcs and see if we can get from S to T. So I'll start from over here because it's kind of easy to see that there's only one arc connecting to T. It's this one here. So if I follow this one back here, now I look from B. Okay, well I can get from B this way, and that's a path, that's an ST path here, S to B to T. I don't know how we want to write that out, but there's that, and we see 3 plus 3 is 6. So that's cool, that's the shortest path because this is also 6. But there's also another one here. Shortest paths don't have to be unique. You can go here, here, and then all the way over here. Because this is 1 plus 2 plus 3 is 6. So we have S, A, B, T equals 6 is also a shortest path. And just because it uses more lines, it doesn't matter. We're looking at the edge weights here. Whereas if you hear of something called the cardinality case, that's where all the edge weights are 1, and that's where we're simply counting up edges. But this is not the cardinality case here. So I hope that helps you. I've already gone way more than I hoped this video would be, but I hope this is helpful to you, and I hope to bring more of these to you. Thank you.